Hello and welcome to the lecture on distribution for the statistics class at Regent University. We're going to be talking about the different shapes of distributions as a way to understand the best way to think about the assumption of a bell curve, right? So most statistics assume what's called normal distribution, which means a nice, beautiful, normal bell curve, right? Now, this would not be a bell curve, as you can see. This would be something called rectangular. It means that every value on your scale, say you have a scale that runs from 0 to 140 there on the bottom, has the same frequency, which means you can't tell where everyone's supposed to be. There's no probability here whatsoever. It's not that, oh, well, like in a bell curve, people are probably in the middle and less likely to be on the edges. In this distribution, people are probably anywhere, right? It could be anywhere because it's an equal amount of probability across. So this is not what you want in statistics. If you're trying to run statistics, the assumption is that you actually have a normal distribution. So what does that look like? Well, this is a beautiful normal distribution shape, right? What you have here is something that's unimodal. It only has one mode. The mean, median, and mode should be exactly lined up. In fact, if you have a perfect normal distribution, the mean, median, and mode will be the same number. So only one top to your mountain there, right? Unimodal. And it's just really pretty. In fact, if you were to take this, cut it in half and flip it over on top of itself like a burrito, then you would find that the right hand side equally matches the left hand side, right? Like the line is perfect if it is a perfect distribution, right? It's not that it's not leaning, this mountain's not leaning to the right or the left. It doesn't have two peaks, it only has one peak, and it's just this beautiful normal shape. Now, of course, this is not really normal. Distribution is not normal in psychology research. No data is perfectly normal. So this is not so normal, right? This looks like a real life mountain, right? Where you might have two high points or two, what we call bimodal. This is a bimodal distribution. You kind of have a major and a minor mode, meaning that it rises in one and it rises again. When I used to teach at a large university when I was in graduate school, we often would say that those students were bimodal distribution. There was a whole group of students who were excellent A students, and then there was a whole group of students who were like CD students, and there weren't very many B students, right? So there was kind of this strange distribution of a bunch of students who went there because it was local or they had some reason, and then a bunch of students who were kind of getting the opportunity to go to college and were struggling, or they had a lot of outside things keeping them from getting good grades. So you had this bimodal distribution. So that can be reality. Sometimes that is the real distribution, is bimodal like this, but it's very hard with a distribution like this to make any probability statements. Where should people probably be? Like, in fact, the middle of your bell curve there is actually a low frequency, right? So like if it was a normal curve, they'd be most likely to fall into the middle of the curve. But in this one, they're actually most likely to fall to the left and then some to the right. So it's very difficult to do research with this. So the other thing you're looking at is symmetry, right? So if you know Denzel Washington, right? If you've ever seen Denzel Washington, particularly when he was young, he has such a beautiful face. He has this very lovely face. Uma Thurman is also said to have an almost perfectly symmetrical face. If you were to cut the face down the middle and flip one side on top of the other side, the eyes would perfectly line up, the nose, the mouth, the cheeks, like all the dimensions for Denzel Washington and Uma Thurman, they perfectly line up. It's beautiful. Humans love that, right? The rest of us, like, one eye is a little bigger than the other, one eye is a little higher. Like normal people, it's not quite symmetrical. But if you have symmetry, then you have a perfect normal distribution. So one of the things you're looking for in a bell curve is it symmetrical? Is the left side and the right side kind of rising up at exactly the same rate or very similar rates, close to symmetrical? Or is it perfectly symmetrical, which pretty much never happens, or is it not symmetrical at all? So here we have the issue of symmetry, and particularly with skewness, right? So when something is not symmetrical, it is skewed. And what you have here are 3 pictures of 3 different types of skewness. The one in the middle is your nice normal bell curve, right? There's no skew there, right? It's symmetrical. Left and right are the same. The mean, median, and mode are all right there in the middle. It's unimodal. That's beautiful. Okay. Then on the right-hand side, you have the positively skewed, right? And so I always think of these and remember by looking at them as where the tail of it is. So if the tail is towards the right, then it's positively skewed. And if the tail is towards the left, then it's negatively skewed. So follow the tail to remember whether it's positive or negative when you're looking at the picture. But this also gives you interesting additional information. So if it's positively skewed, then your mean is going to be higher than your median and your mode. And then it goes the opposite way for negative skew. The mean is going to be lower than your median and mode, right? So this gives you information about descriptive data, asymmetry, all of that. And when we do analysis in psychology research, we actually get a skewness number. We get a single number that tells us how symmetrical our bell curve is, right? The data that we're looking at for any continuous data. So if that middle normal one right there in the middle of your screen, that would probably have a skewness of 0 because it's basically perfect. So a skewness of 0 is a perfect bell curve. Everything is perfectly symmetrical. So the ones on the left and the right are going to go further and further away from 0, right? And in general, when you get a printout and your output, you're going to get numbers. So -1 to 1 is good. Sometimes -2 to 2 is acceptable. Your textbook talks about this with Mertler and Vanetta some. I tend to pick -1 to 1 in my labs and quizzes and tests in my class as kind of a standard. Every once in a while, people will be more strict and they'll do like -0.5 to 0.5, like that. Okay. So that gives you a sense of skewness. Very important data when trying to determine whether you have met the assumption of normality, which means that you have a nice normal bell curve. All right. The other thing you can have is something called kurtosis, which is how skinny is your distribution, right? How much is it bunched up all into the center or spread out all on the ends, right? So the perfect, nice, normal distribution is called mesokurtic. It's in the middle, right? It's meso meaning middle. Lepto means narrow, right? So leptokurtic means that your bell curve is all bunched up in the middle. And we'll look at a picture of one in a second. And platykurtic is all spread out towards the ends. Fortunately, they picked a really fun word because plata means flat, which I always think of platypus, right? So I think, oh, if it's platykurtic, that's platypus. Platypus has a flat bill, right? So it's flat, it's spread out. So that helps me remember, oh, it's like all spread out. It's a low mountain versus a leptokurtic, which is a tall, skinny mountain, and mesokurtic's in the middle. Again, here we get numbers for kurtosis. -1 to 1 is good. -2 to 2 is acceptable. You start getting some weird shapes when you get like a 5. You would actually have the ends higher than the middle. You'd have a bell curve that's like upside down, like a U shape. So, excuse me, this data will really tell you some important things about what your data looks like and how normal it is. So here's our picture, all right? So the platykurtic is the lowest one there that you can see. So it's most flat, like a platypus bill. The mesocurtic is nice, pretty in the middle, and the leptocurtic is a little more bunched up towards the top. It's higher in the middle, and it's got smaller standard deviations, right? It's all kind of bunched up together in the middle. Platycurtic's going to have a large standard deviation. Leptocurtic's going to have a small standard deviation. So this is important information to understand, and that is a Z-score. A Z-score is another way of looking at distribution on your data, and each individual person can get a Z-score for any continuous variable. So you could take everybody's height, which is a continuous variable, right? I'm 5'3", for instance. And we could figure out how many standard deviations am I from the mean. So I'm probably like negative something. I'm shorter than the average woman. So my standard deviation, my Z-score would be in the negative zone, right? Let's say, I don't know if this is true, but let's say 5'3" is one standard deviation below the mean score for the average human. Then that means that my Z-score would be -1. Right? My Z-score for 5'3" would be -1. And every woman that is 5'3" would have a Z-score of -1 if that is one standard deviation below the mean on women's height. Right. And you can calculate it. It's the individual score minus the mean score divided by the standard deviation. If this is like totally new news to you and you've never heard of a Z-score before, Khan Academy has some nice things for 12th graders to catch you up on normal distribution and the Z-score practice. So I recommend it if you need that. You also can look in your Selkind textbook on chapter 8, and it has a really nice walkthrough on Z-scores. For my class, you should be able to do a Z-score calculation as found in chapter 8 practice questions for any tests or homework for me. But again, it's just the individual score minus the mean score divided by standard deviation. Once you understand the idea behind it, from now on, SPSS on the computer will do this for you forever and ever, because why would you do Z-scores for every individual person in your study? But what Z-scores do is they help us to think in terms of standardized scores. It's a standardized score versus the raw score. So 5'3" is my raw score. Meaningful, helpful, but to compare me to everybody else, it's more helpful to know, oh, she has a Z-score of -1. I can put all those together and I can now compare how many people have, are taller, one standard deviation taller. Well, that's at 5 foot, whatever, right? And so you can kind of like line up your Z-scores with your raw scores, and then you can know where your standard deviations are in terms of standard deviation. It's even more important when the number that's given, say a total scale score on a test, is not meaningful, right? So someone scores 45 on this test of depression or something, and you don't know what that is. Like, what's a 45? But if you know the Z-score for that is -1.5, well, they're 1.5 standard deviations below the mean on depression. So I don't know, is that good or bad? Depending on whether high scores are good or bad, but it lets you know, oh, they're kind of like moving out, starting to move, not far, but a little bit outside of the middle of that bell curve, right? So it helps us to think in terms of bell curve. Normal distributions make analysis easy, right? Because skewness in particular is a real threat to data, and we have a big problem if we have a lot of skewness, but it's hard to control. We want things to be symmetrical about the mean and not be skewed. We want the values in the center of the distribution to be the most probable outcomes, with the tail, right, of the bell curve to be the least probable outcomes, and all of probability theory is built on that assumption. Normal distribution, however, is a family of distributions, some of which are a little more funky than others. So a perfectly normal distribution is unimodal. It has no skew or a skewness of 0 and is mesocurtic. And then the mean, median, and mode of a perfectly normal distribution are the same value. Okay? So important information to know. The other thing you can know if you have a normal distribution is you can tell the percentage, right? So this is a picture of a perfectly normal curve, and there is the red, green, and blue areas. One standard deviation is the red area. And this is about 68% of the population on anything that's normal. Anything we measure that's normal, about 68% of the population falls within one standard deviation of the mean score, right? So that's a large percentage, it's almost 70% of people. This would be considered average or normal. You might think of this as like an IQ score or even a depression score, like what's normal? Are they falling in the normal range, right? About 95% of the population falls with the red and the green area together, right? So the green area is from 1 to 2 standard deviations. So about 95% of the population is within 2 standard deviations of the mean in a normal distribution. So anybody outside of that, more than 2 standard deviations, is definitely starting to become unusual. If someone's scoring more than 3 standard deviations from the mean, we start to think of them as an outlier. And outliers are really important concepts in psychology. We love outliers. I love people who are unusual and like not the same as everybody else. They make the world a much better place, but they also are, improbable within our probability theory. The nice thing about normal distribution, and when you have a perfectly normal distribution, you can get these probabilities. Oh, they're 68% of the population, 95, 99. Those are things to know and remember, that 68, 95, 99. Most psychologists kind of know that as a fact of psychology, shows up on the EPPP and a comps exam pretty commonly in our program and in EPPP for psychologists, the national licensing exam. So how do you know whether your data that you have in any study, whether your dissertation or whether a lab for my class, when you're given some data, how do I know whether that is normal data or not? SPSS programs will give you a score to evaluate that distribution. And you can look at several things. One, you can look at the standard deviation. So you should always look at the standard deviation, and it will tell you how spread out the bell curve is. If you have a very large standard deviation, you have more platykurtic, right? It's spread out. It's a big standard. So if that red zone is large, right, then you have a very big, platykurtic kind of thing. It's getting flatter. If you have a very small standard deviation, then everything's all bunched up together in a very small range. And so you might probably have a leptokurtic bell curve going on there if it's a small standard deviation relative to the range. Skewness is a number that tells you how much your bell curve is leaning to the left, which is a negative skew, or to the right, which is a positive skew. And you like to see -1 to 1. And skewness in particular is one that we are going to be watching all semester for all continuous variables as an indicator of normality. And when skewness is outside of that -1 to 1 range, you're going to have to fix it. It's like such a big problem, you can't just leave it there. And then kurtosis tells you how much things are bunched up in the middle of your bell curve versus spread out. Also, if things are bunched up in the middle of a bell curve, even like it's a really small curve, even small differences will show up as significantly different. Whereas if you have a very big bell curve, very flat, platykurtic, it takes a pretty big number difference to move, to 2 or 3 standard deviations from the mean that way. And so it's going to take big differences to see differences between groups. Okay, so just some pictures so that you can see it. I know I'm a pictorial learner myself. What you have here is just standard deviation numbers and what those curves look like. So the red one there has a standard deviation of 0.5. The blue one has a standard deviation of 1, and the green one has a standard deviation of 2. So you can see there how standard deviation numbers, as they go up, you get more platykurtic. As they go down, you get more leptokurtic. Right. And this is just like made up numbers, right? For it. Sometimes standard deviation, you have to really kind of look at that in terms of the rest of your data. While it's standardized, it still is pegged to the data you have, whether you have a 100-point scale or a 5-point scale or whatever. I'm finally going to show you skewness and some pictures on that. What we have here is some data from a study that I've done. This is a study of couples and couple therapy. And what we have here are 3 different variables. And I've highlighted in yellow the actual skewness data that SPSS will give you. And you can see to the right of that, the kurtosis, and to the left of that, the standard deviation. So you actually have like a lot of information here in this simple descriptive statistic output. So one of the questions that we asked was, did you experience your couple counselor as warm, right? And we asked that at long-term follow-up, which was 2 to 10 years after they finished therapy. And we have there a very negative skew, right? A negative skew because it's negative 1.359 or rounded negative 1.36. That's not good. It's outside, right? It's lower than -1, right? It's not between -1 and 1. It's outside of that. And you can look at the histogram picture there and see the negative skew there. It's kind of good outcome, right? Like, so like the vast majority of couples rated their counselor as a 4 or 5 on a scale of 1 to 5 there as to whether or not they were warm towards them, like interpersonally warm, and very few rated their counselor as a 2 or a 3, no ones. So that makes for a negative skew. So if we needed to analyze that data, we might need to fix it because it is not good. It is a negative skew. That's poor. Here's another one. This is the second one, the RCS. This is a relationship commitment measure. These are really commonly negatively skewed because people who come in for couple therapy tend to say anyway that they're highly committed to their relationship. So you can see that there. It runs on a scale that goes from 4 to 20. Nobody scored a 4, right? But lots of people scored like 17 and above, right? We've got pretty high numbers there on the right-hand side. So again, we have another negative skew and you can really see it. Look at that number. Negative 1.935 is the skewness number. But notice that the standard deviation is larger for this one, 2.6, because the scale is larger because it runs from 4 to 20. Whereas the last one, the scale only ran from 1 to 5. So it's a smaller standard deviation, but it's still pretty big compared to the whole scale, which was only 5 points. This one has a standard deviation of 2.6 on a scale that's running 16 points, right? So it's, you know, it's kind of more spread out that way. You can even see the kurtosis. The kurtosis on the commitment scale, the RCS, baseline RCS, is larger, right? So it's a little more bunched up together than the experiences in close relationships one. So, but this also problematic. We would not be happy with this. We weren't happy with this with 108 people that filled it out. And so we had to, we'd have to do something called transform it, which we'll be covering later in the semester about transforming non-normal skewed data. And then finally, this is a beautiful one. And we have a skewness here. You can see of a negative 0.446 or rounded negative 0.45. This is the RDAS. This is the Relationship Dynamics Assessment Scale. This is a classic satisfaction measure. So this is how satisfied are you with your relationship? And while we have a little spike there with a lot of people scoring, looks like around 50, right? For some reason, that one kind of spiked a bit. Overall, it looks like a pretty normal curve, right? You can kind of see it going. And in fact, when you draw the curve to fit it, you actually look, yeah, that looks pretty mesokurtic. It's unimodal in the curve anyway. And it's, you know, fairly pretty. So that's why you have a skewness of negative 0.446. It's not perfect. It's not a skewness of 0, but it's nice. And a skewness of that number would indicate to us that we have normal data. Now, another reason why this data actually is good data for us to look at is because if you look at the N, so this was a study that was done across 15 years of data. So we have different numbers. And the only thing that has like good data out of every single participant is their baseline adjustment scale score. So the RDAS, which is the relationship adjustment, that's all participants. 472 people filled out that questionnaire across 15 years. So we have a very large N, and the skewness tends to be pretty good. Normality tends to be pretty good with a large N. When it went down, now commitment all on its own has a tendency, and here we'll look at it, commitment has a tendency at 108 people, you're probably going to have a harder time finding normality. Although that's still pretty good sample size. It's not bad. But commitment just naturally tends to skew negative, right? People tend to be pretty committed when they're seeking marriage counseling anyway. And then finally, we have an even smaller sample because these are people that filled out our questionnaire about that particular question like years later, right? So we tracked down, we actually tracked down 100 people years later, but only 25 of them had answered this warmth question originally. And so that one is a really pretty small n. So it's kind of not surprising that we don't have much spread here. It's also a really small scale. It only goes from 1 to 5. So it's easier to end up with some skewness, and people tend to like their therapists. So you tend to get a natural skew too. So I hope that that's helpful for you to kind of understand what it actually looks like for skewness. Finally, these are the takeaways from this lesson. First, a perfect normal distribution is the assumption based on probability theory applied to all continuous variables or quantitative variables, it's kind of scales. So nothing that's categorical like gender or something like that, but continuous. The further the shape gets from normal, the bigger problems we have. We can measure particularly symmetry with the measurement of skewness, and a skewness score of -1 to 1 is generally considered good, and you're happy with that. You want to know positive and negative skewness. And for my class, you want to be able to look at a picture of a bell curve and be able to label it. Hey, that's positively skewed or negatively skewed. Oh, that's platykurtic. That's mesokurtic. That's leptokurtic. All of that. And I should be able to show you pictures and you would go, okay, I know what that is. You should be able to calculate a Z-score, right? And how it relates to standard deviation and understand that. And you should be able to understand that percentages below the curve concept in the normal distribution with the red and the green, the 68, 95, and 99%. That shows up on your EPPP test and the comps questions quite often. So it's one of those things that all psychologists learn. So I hope that this was helpful to you and that you have learned a lot from this recording.